Okay, let's start. Yeah, so we are trying to look at the proof of Stone's first representation theorem. It's for finite Boolean algebras, and so far we have seen these things, that given a finite Boolean algebra B, we know that it is atomic, so let X be the set of atoms of B, and we are trying to prove that this map H defined from B to the power set of the set of atoms by X mapping to all the atoms sitting below X. Yeah, so that particular map is a surjective order embedding, which means an order isomorphism. And in the tutorial you will show that an order isomorphism between two Boolean algebras is precisely also a Boolean algebra isomorphism. Okay, so we need to prove three things. It is surjective, it is order preserving, and it is order reflecting. Okay, so let us show the first one, that H preserves orders. So suppose X is less equal Y, then what will happen? Then what can you say about dx and dy? The downset of X? Downset of X is a subset of X, and therefore when you take intersection on both sides with the set of atoms of B is also contained. And therefore H of X is a subset of H of Y. Very simple. Now the second thing, H reflects order. So in order to prove that H reflects order, we will in fact prove the contrapositive. Okay, we will say that if X is not less equal Y, then Hx is not a subset of Hy. Now this method of proof, this I want to highlight, this method of proof is very common in Boolean algebras, because we convert a meta level statement, that Hx is not as less equal Y, a meta level statement, we are saying that something does not happen, that we will convert into an internal negative statement. The internal negative statement means that we will convert it into a statement about complements. Complement is the internal negation, and we are saying this statement does not happen, that's external negation. Okay, so therefore this method of proof is very commonly used for Boolean algebras. Okay, so suppose X is not less equal Y. See, this is, I am not saying that X is strictly less than Y. Yeah, this not goes across the less equal sign. What happens, do you remember? We proved one result last time. X is less equal something if and only if something else happens. What was the result? You remember this? X is less equal negation Y if and only if X meet Y is equal to 0. Right. So now we also proved one more result, that double negation Y is equal to, very good. So now tell me, what should I conclude from here? If X is not less equal Y, then X is not less equal double negation Y. So therefore X meet negation Y is not 0. Okay, now look at this particular statement. B is atomic. What is the meaning of being atomic? What is the definition of atomic? For every non-zero element, there exists an atom below it. So therefore now we got something non-zero. X meet negation Y is non-zero. So since B is atomic, there exists A in the set of atoms such that A is less equal X meet negation y. Yes, because it's non-zero, some atom must exist below it. Okay, what do we know? If A is less equal meet of two elements, then A is less equal both of them. Yes, so therefore A is less equal x and A is less equal negation y. Now what will happen? So we claim that A is not less equal y. See, what will happen? If A is less equal y, A is less equal negation y, then A is less equal their meet. And what is meet of y and negation y? 0. But A is not 0. A cannot be 0. A is an atom. Atom is a non-zero minimal element. Okay. Yeah, so otherwise A is less equal y meet negation y equal to 0, a contradiction. So by the claim, what do we know now? So therefore A belongs to downset of x. Yes, we said that A is less equal x, but A does not belong to the downset of y. Correct? So we got that. A is an atom which belongs to downset of x but doesn't belong to downset of y, and therefore A is in H of x but not in H of y, and therefore H of x is not a subset of H of y. Done? We found an atom which was below x but not below y. That's precisely what we needed to show. Okay, what is the third property? H is surjective. Okay, how do we prove H is surjective? So let us start with something. First, let us observe, first note that H of 0 is what? No, H of 0 is not 0. H of 0 is the empty set. Here 0, by 0 I mean the least element of the Boolean algebra, not our von Neumann ordinal 0. Right? So 0 is the least element, so H of 0 is equal to empty. So we can start with something in the codomain which is non-empty. So let S equal to A1, A2, An be a non-empty set of atoms of B. Yeah, I mean, let me quickly remind you that our target is the power set of the set of atoms of B. Right, so I should choose a subset, but I already argued that for empty set the map is surjective. For non-empty subset of the set of atoms, we need to show this. Now can you tell me, yeah, if you remember from our 3 atom picture, 8 element Boolean algebra picture, how to construct some x which will map to this element S. What should we do? We should take their join. Don't say union. Union doesn't make sense. So let x be join of S, which means A1 join A2 join An, and we are going to claim that H of x is equal to S. So what do we need to show for showing two sets are equal? Both are subsets of each other. Okay. So clearly AI is less equal x for all AI in S, right? Because we are x is their join. So join is always bigger equal the original element, and therefore ai belongs to h of x for all ai in S, and therefore S is a subset of h of x. Yeah, nothing over here, nothing complicated. So what is the next thing that we should show? Suppose there exists, yeah. So suppose A is less equal x and A belongs to the set of atoms. Then we need to show that A is one of the AIs. Yeah, then we will complete the proof. We need that A is equal to AI for some AI in S. All of you agree with that? Okay. So we are not going to show A is equal to AI. We will slightly modify it to an equivalent statement. Yeah? We will show that A is less equal AI for some AI in S. Okay, so now think about this. Atoms are always non-zero minimal elements. Even if I say A is less equal AI, what do I get? Equal. Because A cannot be 0, it always has to be equal. Okay, so simple idea. A is less equal AI. Suppose not. But now because we have less equal, we can use something different. Okay, I am writing a result in green again. Yeah. So if A is an atom and X is any element, then either A is less equal X or A is less equal, yes, complement of X. A is less equal negation of X. Yes, we mentioned this result last time. So then A is not less equal AI for each AI in S. Yes, by the green result now, by the green result, yeah, I mean in exam please don't write green result. By the green result, what do we conclude? That A is less equal. If A is not less equal AI, then A is less equal for each AI in S. So then what will happen? If A is less equal negation of a finitely many elements, then A is also less equal their meet. Yeah, it's a common lower bound, so it should be less equal the greatest lower bound. So therefore A is less equal the meet of negation AI where AI belongs to S. All of you agree? Okay, but now use De Morgan. So by De Morgan we can take this conjunction meet inside, and what will that meet become? A join. So negation of join of AI in S. Okay, but what is join of AI? We started with X. So what did we obtain? A is less equal negation X. Now what happened? See, originally we said that suppose A is less equal X, and now we concluded that A is less equal negation x. So therefore A is less equal x and A is less equal negation x. This implies that A is equal to 0, which is a contradiction. So our assumption is wrong, and therefore A is less equal AI for some AI, and that completes the proof. Yeah, we have shown that Hx is equal to S, right? Okay, as a simple corollary, if B is a finite Boolean algebra, then what is the size of B? It should be a power set. What is the size of power set? 2 to the power n for some n bigger equal 1. Any problems in Stone's representation theorem? Good. So let's go to the next concept now, that is subalgebra of a Boolean algebra. So suppose B and then dot dot dot, yeah, I mean dot 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 means right, meet, join, negation, etc. is a Boolean algebra. Say that B dash subset of B is a subalgebra of B if, I mean, to be very clear, I should say that B dash subset of B is the underlying set of a subalgebra of B if for all xy in B prime, x meet y, x join y, and negation x, they all belong to B prime. Okay, all these three types. So basically that subset is closed under meets, joins, and negations. And 0 and 1 also belong to B prime. I mean 0 and 1 as in the original 0 and 1. See, what could go wrong? I can draw an example. You remember this example? Now, I can suddenly say that only these red things, that is a Boolean algebra. It is a Boolean algebra by itself, correct? Because it has a least element, it has a largest element, then it has only one other element and its complement. So it's a Boolean algebra, but it is not a subalgebra. For it to be a subalgebra, it should get everything induced. Induced as in from the parent Boolean algebra. The parent Boolean algebra is the green one. So it must contain this one, this 0, and it should be closed under join, meet, and negation. It cannot have its own negation operation. It cannot have its own join or meet operation or its 0 and 1. Okay? So one such example always is that 0, 1, yeah, I mean we write it as 2, is a subalgebra of every Boolean algebra, correct? 0 and 1 of any Boolean algebra, they will always form a subalgebra. Okay, another example, that PFC, the finite and cofinite subsets is a subalgebra, because not only are we saying that it's a subset, PFC is a subset of PX, we are saying that intersection of any finite or cofinite subsets, union of any finite or cofinite subsets, as well as complement of any finite or cofinite subset is again so. Yeah, so therefore it is a subalgebra. So ultimately, what do we want to prove? I will write one theorem. So this is Stone's representation theorem. I mean, this is the infinite case. If B is an infinite, I mean the word infinite is not really important here, the proof also works for finite. If B is an infinite Boolean algebra, then it is isomorphic to a subalgebra of Px for some x, for some infinite set x. So in general, see, what we are not requiring that every Boolean algebra is power set algebra. We are saying a slightly weaker statement. We are trying to say that it is isomorphic to a subalgebra of the power set algebra. Are you convinced that this should be the case? Consider, okay, tell me, what is the power set of natural numbers? What is its cardinality? 2 to the aleph naught. So, can there exist a power set which is countably infinite? Power set of real numbers is countably infinite? Power set of real numbers means 2 to the aleph naught. It's certainly not aleph naught. So, there is no power set which has cardinality aleph naught. However, come back to this, PFC X, the collection of finite subsets of natural numbers is in bijection with the collection of cofinite subsets. Yeah, simply take complement. So therefore, the cardinality of PFCX is precisely twice the cardinality of Pfin of X. Understood? But what is the meaning of twice in cardinal arithmetic if you go to infinite cardinals? It's the same, right? So I am arguing, yeah, so note that PFC X is Pfin X disjoint union P cof X, cofinite, and Pfin X is in bijection with P cofinite X. So therefore, if X is infinite, then PFCX, its cardinality is 2 times cardinality of Pfin X, Pfin N, sorry, I should say Xn here, oh wow. Two times cardinality of Pfin N. But what is the cardinality of Pfin N? The set of finite subsets of N is in bijection with N. So therefore this is 2 times aleph naught, which is aleph naught. Okay, so now are you convinced that in Stone's representation theorem we actually need to talk about a subalgebra. Right? This is a subalgebra of the power set algebra. We cannot directly say it's isomorphic to a power set algebra. Now, also remember that there is a Boolean algebra which is atomless. Okay, I haven't told you what it is, but there is an atomless Boolean algebra. So, can our previous proof work? We found the set X by, what did we do? By choosing the set of atoms. But if there is a Boolean algebra which doesn't have atoms, how do we find set X? Are you understanding the problem? That we need to look for something else rather than finding atoms. Okay, now come back to this example. I am going to use a blue color, and you tell me what is the upper set of this particular blue element. Is this in the upper set? This in the upper set? Yes, and this element. So I am going to mark 4 blue points. So one observation that you should make, we started with an atom. What is its upper set? How many elements does it contain in the upper set? 4? In an 8 element Boolean algebra, the upper set of an atom consists of 4 elements. So you can say that it contains exactly half of the elements. If we can figure out what subsets can be like this blue subset, then we will be through. Because subsets are always a property. Yeah, subsets will always exist for a Boolean algebra. Even though atoms need not exist, subsets will exist. Any question? So let's go here. Before I give that definition, I also want to ask you, if P is a prime number and it divides product of 2 natural numbers A and B, then what can you conclude about A and B themselves? Okay, so just remember this, okay? I am not going to talk about it right now. And this is an important property of prime numbers. Okay, so I am going to define the blue subsets. So those subsets are called filters. A subset, what should be the notation for a filter? F, correct. A subset F of B is said to be a filter of the Boolean of a Boolean algebra B if, now it must have some properties. First of all, we do not want filters to be empty, and they should always be upper subsets. You understand upsets? Upsets means if an element is there, then all its upper bounds are also there. Okay, so first thing I will say, if upper bounds are there, then in particular one should be there. If I want it to be non-empty, then the first property is that one must belong to F. Second property, that F is an upper subset, i.e. if X belongs to F and X is less equal Y, then Y also belongs to F. And the third property, okay, so far what we have defined is just an upper subset, non-empty upper subset. But we want to distinguish between those upper subsets which are special, which are filters. So what's the next property of a filter? That if x comma y belong to F, then x meet y also belongs to F. So not only are they closed under all upper bounds, but they are also closed, like if there are two elements, then their meet is also there. Something smaller also exists there. Once again, I am going to draw an example because otherwise you won't understand what's going on. Very simple example. Can you describe all filters in here? 0, A, negation, A1. Singleton 1. Singleton 1 is a filter, very good. Okay, what about other filters? A1. Then negation A and 1 has to be there. And if I put A and negation A both, then by this third property 0 should also be there. Well, generally we are not interested in filters which contain 0. How many can there be? Only one, the entire Boolean algebra. So therefore we'll say that a filter is proper. Filter F is a proper filter if 0 doesn't belong to F. And almost always we will talk about proper filters. Okay, so you can find out filters. I will go back to the previous screen, and can you tell me some filters over here? If I include this yellow, these two yellow elements, then you should include this point because it's the meet, and you should also include the top element. Now if I include this element, then suddenly it will explode. See, this is an important property, that if you go beyond half, then it becomes improper filter, it becomes everything. Understood? Beyond 4 elements this will explode, beyond 2 elements this example also exploded. There is nothing like 3. For 8 element Boolean algebra there is nothing in the cardinalities 5, 6, 7. If it's beyond 4, then it's suddenly 8. So this property is called being maximal. So a proper filter F is maximal if F prime is whenever F prime is a proper filter and F prime contains F. Then what should happen? It's maximal. So with respect to inclusion. So then F prime is equal to F. So in a finite Boolean algebra case, maximal filters will contain exactly half of the elements. You understand that? It contains exactly half of the elements. So for example, this yellow thing, this is a maximal filter. If I add anything else to it, it will explode. Then yes, this yellow thing, it is a maximal filter. In fact, every maximal filter contains, every maximal filter in a finite Boolean algebra contains a unique atom. Correct. So I will write that statement. every maximal filter in a finite Boolean algebra contains a unique atom. So basically the set of atoms of a finite Boolean algebra is in one-to-one correspondence with the set of maximal filters. Yeah, that's what this note says. So we have got a candidate for set X. Yes, we want to show that every Boolean algebra is isomorphic to a subalgebra of some power set algebra, but power set of X. What is X? X is the set of all maximal filters. Maximal filter by definition is proper. However, okay, before we go there, we are going to modify this definition only a bit. So, a proper filter, I am going to give you two more definitions. Yeah, F is prime if whenever X join Y belongs to F, then X belongs to F or Y belongs to F. Whenever join of two elements, two elements are coming from the Boolean algebra. Whenever their join is in F, then X is in F or Y is in F, and why is it called prime? Because of the first line. See what happens there, I will rephrase it. So whenever AB belongs to PZ, PZ means all the prime, like multiples of integers, multiples of P, integral multiples of P. This implies that A belongs to PZ or B belongs to PZ. So in this case, PZ is called, in algebraic language, it's called an ideal. It's a prime ideal of the ring of integers. Okay, that's the property, and the same property we are using here. If X join Y belongs to F, then X belongs to F or Y belongs to F. There is one more definition. A proper filter F is an ultra filter if for each X in B exactly one of X and negation X lies in F. This is more in connection with our earlier understanding, that for a finite Boolean algebra with 8 elements, only 4 elements lie in the proper filter. What do you expect are the connections between these three notions, maximal, prime and ultra? A proper filter is maximal if and only if prime, if and only if ultra. They are not different at all. They just talk about different properties. So observe here, in this yellow example. So what is the negation of 0? Okay, so 0 and 1, exactly one of 0 and 1 lies in the yellow part. A and negation A, exactly one of them lies in the yellow part. Right, so it's an ultra filter. then join of A and negation A is 1. So A and negation A, join of them is 1. So by prime property, either A is there or negation A is there. Yeah, we have chosen A to be in there. So prime, ultra, maximal, it doesn't matter, they are all equivalent notions. You will prove this in the tutorial. But this is our set. Okay. So now we are ready to go and show this particular property. This Stone's representation theorem, the infinite version. Now the proof here is very similar to our earlier version, but we don't prove surjectivity. We only prove it preserves order and it reflects order. Okay. So now it's a common practice. Yeah, I'm going to give you some advanced notation. Let spec of B denote the set of all prime filters of B. Okay, the set of all prime filters of B. Spec stands for spectrum, and this is a commonly used terminology because spectrum is also equipped with a topology. Maybe you haven't heard of this term, but spec B can be equipped with a topology so that the thus formed topological space is called Stone space, and that's an important object of study. But let's not go there right now. It's just a set. Spec B denote the set of all prime filters of B. Define H from B to the power set of spec B by what will I send it to? X mapping to X is a single element of my Boolean algebra. I need to send it to some collection of some set of prime filters. Which prime filter should I send it to? Yes, very good. So all those F's in spec B such that they contain, yeah, there is only one natural choice, or you could have chosen X not in, but yeah, they are equivalent. Okay, we will show H is an order embedding. Okay, the first thing, what should we do? So first thing, that H is monotone, order preserving. So suppose X is less equal Y. What do we need to show? That Hx is contained inside Hy. So that means all those filters which contain X must contain Y. Okay. So let F be a prime filter B such that X belongs to F. So basically we have assumed that F belongs to Hx. Yeah, I will write that in the bracket, i.e. F belongs to Hx. Then what will happen? If X belongs to F and X belongs to F and X is less equal Y, then Y belongs to F. Since F is an upset, correct? It's closed under upper bound, so x is there and y is an upper bound, so it must contain that. Okay, therefore what do we conclude? So y belongs to f, therefore f belongs to and therefore h of x is a subset of h of y. Done? Very simple proof. Conversely, h is order reflecting. Again, what would be our idea? We prove the contrapositive. Yeah, so suppose x is not less equal y, then by the same green property that we wrote earlier, x meet negation y is x meet negation y is not 0. So consider the upper set of x meet negation y. Every upper set of every principal upper set, yeah, this is the principal upper set. Every principal upper set is a filter. Okay, let me write it, prove it as a homework. Every principal upper set is a filter, and if A is not 0, then UA is a proper filter. Right, because UA cannot contain 0. If A is non-zero, then the upper set of A cannot contain 0, so it must be a proper filter. Now, okay, we are not done yet. So far, we have just obtained a filter. But what do we really need? We need some what do we need? We just have a filter. We need a prime filter. We need a prime filter. See, we started with x not less equal y, so we need something that is in h of x but not in h of y. Which means we need a prime filter which contains x but which does not contain y. Understood? Okay, so we need some prime filter f such that x belongs to f but y doesn't belong to f. Now here I am going to utter the word magic. What does that remind you of? Zorn's lemma. Okay, so actually this is an important statement. I will write it on the previous slide. So this is what we call Boolean prime filter theorem. It says that every proper filter f can be extended to a prime filter. F dash, yeah, I mean extension means that it contains f. So if I am given a prime filter, if I am given a filter which is proper, then I add more elements from here and there. I don't know how. Yeah, I mean, that's the magical part, because we only know partial information and then we complete it to another level of information, and then we complete it to a prime filter. Yeah. So prime filter is also maximal. So if you remember that we needed a maximal linearly independent set. Yeah. So maximal filters, we converting every proper filter into a maximal filter, that's Zon's lemma. So use Boolean prime ideal theorem, prime filter theorem. In literature, you will call it Boolean prime ideal theorem also sometimes, because ideals are complements of filters. They are downsets with exactly the opposite property. There exists an F0 in spec such that F0 contains the upper set of X meet negation Y. The upper set of X meet negation Y is a proper filter. Yes? So, I mean, let me write it. This is a proper filter. Why is it proper? By green property. Yes? Because this was non-zero. X meet negation Y is non-zero, so therefore its upper set is proper filter. So therefore, X meet negation Y belongs to F0. What can you conclude? Therefore, X belongs to F0 and negation Y belongs to F0. Now, similar to the claim earlier, I will claim that Y doesn't belong to F. Yeah? If Y belongs to F0, then Y meet negation Y belongs to F0, which is 0, which is a contradiction because it's a prime filter, so proper. So therefore, Y is not in F0 and therefore F0 belongs to Hx but not in Hy, and we are done. Okay, we proved that it is an order reflecting map also. Any questions? Okay, then we are done.